This is Free Range Digital Design Foundation Modeling, Chapter 27. This chapter we're going to look at shift registers, which, as the name implies, it's another type of a register, so it adopts all the features normal registers, but it has some extra features, namely shifting. Once again, it is a type of register. Here's the Venn diagram you've seen before. Registers, we've looked at counters, but here are shift registers, and there's different types of shift registers, or shift registers can actually do many types of different things. And one of them is a barrel shift, which we'll talk about later. The shift registers are, of course, special cases of registers, but they're well known to do two things really well and really fast. And so the issue is they multiply and they divide by powers of 2 very quickly, and essentially they do it by shifting. So a shift register essentially takes the contents of a register and shifts it. For example, if we have this number here, this number is going to be 6. Now what I'm going to do is shift all these bits right and add an extra bit in there, and so that new 5-bit number is this, which equals 3. So necessarily you can see that if I stuff in a 0 there and shift it to the right, it divides by 3. The same idea here, if I have this number 0, 0, 1, 1, 0, and I shift it to the left and stuff in a 0. So this number right here, this actually goes away. This number right here is 12, when this number is 6. Okay, so you can see by shifting all the bits to the left, stuffing a 0, I see it multiply by 2. By shifting it right, stuffing in a 0 on the left side, it's a divide by 2. I can get a divide or multiply by 2 very quickly, and usually in hardware land what we have is multiplication and division algorithms that are computationally expensive. The shift register does these multiplications and divisions very quickly and cheaply. The only issue is the shift. When I'm shifting right, it will, which is a divide by 2, sometimes it will truncate, and the issue is shifting left, and there are really no issues with shifting left so long as you give it enough bits such that it doesn't overflow. So this is the shift register, the general case. What we have is 1-bit storage elements, which typically are modeled as D flip-flops, and the idea here is this happens right shifting. What you see here is data is coming into this shift register on the left side, so this is data from the outside world, and what happens here is each one of these output bits of a given shift register becomes the input bit to the shift register to the right of it. They all share the same clock, so when this active clock edge comes around, the contents of this register go into this register at the same time as the contents of this register goes into this register. What it accomplishes is what everyone knows as a shift. This bit comes from the outside world. It has to be provided. This bit here before the shift is something, but once you shift it, it goes away, so that bit is lost. This is an example of a 4-bit shift register. That's once again that's shifting right. Here's your data coming in from the outside world, and here's the data of the last bit right here. So what you see here on this clock edge, this data right here gets latched into that register Q3. At the same time, data from this 3 here, which happens to be 0 at that clock edge, gets latched into this register, etc., etc. So so do it again. The Q2 here, which is 0, gets latched into this register, and on and on. So every clock edge we see the shifts happening. And so what we see in this diagram is initially it's feeding in a 1, a 0, a 0, a 0 from the left side, and here it's going to feed in a 1, a 1, a 0, a 0. And so what you see essentially is kind of a shifted version of that or the leftmost flip-flop. And you can see it, this shifted here, you can see that thing being shifted. You can see this 2-bit. It's 2 bits because for 2 clock cycles in a row that data input was a 1, which causes this to be a 1 for 2 clock cycles. You can see that shifting and to the right also. Here's a 3-bit example worth going through. This thing is synchronous, so I always, when I have to do these things, I mark these clock edges here. So this is the current state, 3 flip-flops, or the shift register. It's 0, 0, 0. What we see here is I'm sticking a 1 into it on the left side. So after that clock edge, this 1 here becomes that 1 right there. So the next clock edge is a 0. So this 0 right here becomes that 0 right there. This 1 here gets shifted over to here. Onwards and onwards, you can see this the same thing. Here's another 0 here. This 0 becomes that 0. You can see that shifting out. And since there's no 1 input, eventually I get back to 0. But then again, I stick a 1 in there. So this, once again, this 1 becomes this 1 as it shifts to the right. And you can see that 1 shifting through this thing, and that's really why they call it a shift register. And the idea here is, remember, I can shift left or right, but for these hardware diagrams, it's easier just to show a shift right shift register. Actual shift registers, if they just shifted right, that would be pretty useless. What we're going to be working with is what we call universal shift registers, USRs. Fairly simple operation, a little bit harder to describe in hardware, but they're extremely easy to model in hardware description language. Typically, our USR is going to do one of 4 things. That's a hold, that's a load, it is a register. Yes, so we can design the hardware to do all that stuff, but like I said, it's easier to model and let the synthesizer deal with the hardware design. Now, there are a couple different types of shifts out there. We've been talking about essentially simple shifts. There's also barrel shifts, rotates, and arithmetic shifts. Barrel rotates are quite popular in DSP type applications. Rotates are very useful, and arithmetic are pretty much popular everywhere. So that's really simple ideas, and we'll cover that next. These are rotate ideas. It's a shift register, which means it's register. Our shifting operation, as you saw, lost a bit. So you had to stuff a bit in from one side, depending on what side you're shifting, and then you lost the bit from the other side. So if I was shifting right, I have to stick a bit in on the left, and then I lose the least significant bit or the rightmost bit after I do the shift. So a rotate is a little bit different. It's essentially like a shift. For example, for this rotate right, I'm not losing this bit, I'm actually stuffing in to the MSB. In this case, I don't need an extra bit on the left side because I am sticking the LSB on the left side. Right, but a shift left is going to be the same idea, but it's in the different direction. So shifting left, generally speaking, I have to stick a bit in on the right side, and I lose this bit. But what I'm going to do is take that MSB and shove it in the LSB, and that's going to be my rotate. So for both of these rotates, unlike the simple shifts, I don't lose a bit, and I don't need to provide a bit to stuff into it. It uses the LSBs or the MSBs depending on whether it's rotating left or rotating right. The rotates, rotate left, rotate right, those are 2 types of rotates. So barrel shifts are a little bit different. They're very much like simple shifts. Simple shifts shifted 1 bit per clock cycle, but the barrel shifts are set up, essentially the hardware is set up such that it can shift more than 1 bit on a given clock cycle. So there's nothing real magic about it. You actually have to set this up in hardware. This is an example of a right barrel shift that's shifting twice. So you can see that this value right here becomes this value right here, and I'm stuffing in 2 zeros. Now it's the same thing for a barrel shift left. This is an example where I'm losing these 2 bits, but these 6 bits become these 6 bits, and I'm sticking in a 1 on this side. So I end up sticking in 2 1s. So it's very useful, particularly the shift rights, DSP applications. Multiply accumulate instructions in particular use these quite often. Last type of shift we want to look at is the arithmetic shift. Arithmetic shifts are essentially like simple shifts, but I need to protect the sign bit. So what happens is in an arithmetic shift, instead of, like these are shift rights, instead of stuffing a bit in on the right side, what I do is I retain the sign bit and then I propagate it to the right. These bits here become these bits right there, and that's my rotate right, and what I'm doing is propagating this 0, so that 0 becomes this 0. The same idea works for a negative number. This happens to be a positive number because the sign bit or the leftmost bit is cleared. Here's a case where it's set. So in particular, this is another arithmetic shift right. There goes the sign bit. I protect it, but I also send the sign bit over here, and these values right here get shifted over to here. These bits here become these bits down here. So this is the foundation module for a universal shift register. It is a register, so we do have data coming in and data coming out. Additionally, we have an extra data bit, which is that extra bit that we're going to stuff in on the left side for a right shift, and we're going to stuff it in on the right side for a left shift. So this is that extra bit that we need to provide stuff in. It's going to be a data bit. Other than that, we have a clear as we know it. Typically we have an operation select. All the examples we do in this book are going to be, this is X is going to be 2, and we have operation. This is going to be typically a hold. You got to state this every time. Load, shift right, and a shift left. Okay, and it is a synchronous circuit. The clear is oftentimes asynchronous. Typically all the operations governed by the select are synchronous operations. The data in matches the data out on these things as in a normal register, and that is what we have for a shift register foundation module.